Hello and welcome to the lecture of linear algebra. Today we'll talk about linear independent sets and bases. The thing here is we have already talked about linear independent sets in our previous lectures, but uh, this lecture is talks about the linear independent set from the perspective of vector spaces and how it affects the basis of those vector spaces or subspaces. So we already know that index set of vectors, if I say there are p vectors in a vector space, and we assume here instead of previously that there were certain vectors, but now these vectors are part of a vector space, is said to be linearly independent if the vector equation, we know that the linear combination of all these vectors sum up to 0. We say it's linear independent when it has only the trivial solution in terms of C1 to Cp. If it has a non-trivial solution, uh, say if it has a non-trivial solution, it means C1, that the above equation hold for non-zero values of C1 to Cp, then we say this set is linearly dependent. Okay, so this set is linearly dependent. So now for example, just say in Rn a set containing a single vector, let's say v. So there is a set which contains only a single vector v, is linearly independent if and only if v is not equal to 0. Okay, now a set of two vectors is linearly dependent. Similarly, example and as an example, we say that a set of two vectors are is linearly dependent if one vector can be written in the form of other, right? So if one vector is actually a multiple of other vector, so now for example, let's say v1 and v2. So if these are two vectors, now they are linearly dependent if you can write v2 is equals to, say, a times v1. Okay, so we can extend this concept to the multiple vectors. If say v1 to vp are the set of vectors in the vector space, and we assume that any of this vector is not equal to 0, it means if I say v 1 in this, let's say, is not equal to 0, is linearly dependent if and only if some vector vj in all these vectors with j greater than 1, you can write that is a linear combination of the preceding vectors. So we talked about a single vector in a vector space. It can be linearly independent if it is not equal to 0. Similarly, we talked about two vectors in a vector space. If one vector can be written in the form of another vector, then it's a linearly dependent vectors. Now we can generalize this to set of p vectors in the vector space. Say for example, if any vector which is between 1 to p, let's call this vector vj, if this vector is a linear combination of the preceding vectors or other vectors in the vector space, then of course this is also a linear dependent set. Okay. Yeah. To give you an example on that, let's say if I say we talk about p1t, p2t, the polynomials and order polynomials. Remember that we have already covered that in our previous lectures. Let's say p1 of t is equals to 1, p2 of t is equals to 2, and p3 of t is equals to 4 minus t. So we can see here that if this is a set in vector space, then we can see here p3 of t can be written as 4 times p1 minus p2 of t, and this is t. So it means here the vector p3 can be written in the form of one vector of the polynomial of order 1 and polynomial of order 2 for n, not rather order, basically p of n of t. Remember that p n of t. So it can be written as a linear combination of p1 of t and p of t of t. So it means this index set is basically is linearly dependent set. Okay. Now if you remember the last lecture, and there was a set that was sine of t into cos of t. I think it was a displacement equation for the spring is actually linearly independent, right? Because the thing here is sine cannot be written in terms of cos, and cos cannot be written in terms of sine. Okay. Now at least by a scalar amount c. I mean, of course you have to you can write that as a phase shift, but the thing is what you have to multiply is with a constant scalar quantity c, for which it cannot be written from sin t to cos t and cos t to sin t. Okay. Now similarly, but if I say there is a vector set which is sine of t into cos of t and sine of 2t, right? So in this case they are linearly dependent, because you know that sine of 2t is equals to 2 times cos of t into sine of t, and effectively cos of t, you can write this is, let's say, v1, this is v2, so v2 can be written as 2 times actually v1. So by that logic it is basically linearly dependent set. Okay. Now coming to the concept of the vector spaces from when dealing with these linearly independent and dependent sets. So if I say that H be a subspace space of vector space V, an indexed set of vectors B is equals to B1 to BP in V is the basis of H if number 1, B is independent, how can be independent set, and the second one is the subspace spanned by beta spanned by this basis set coincides with H. That is, H is equals to span of B1 up to BB. So the thing here is that if that H be a subspace of vector space V is an index set, then the vectors that basically are in V, these vectors are in V, is a basis of H if and only if they are, this set is actually a linearly independent set. It means any of the vectors cannot be written in one other form, right? So B is a linear independent set, and the subspace spanned by the V coincides with H. That is, H is equal to span of B1 to BB. Last time, remember that we have already defined when you span of two linear independent vectors, they actually form a subspace. So I mean, the thing here is definition. Actually, this definition applies to the case when H is equals to V, because any space is a subspace itself. So we can also say that V is a linearly independent set that spans V. Okay, so here if H is equals to V, so it means the basis of H is same as V, so you can say a basis of V is a linear independent set that spans V. Okay, now to give you an example on that, say for example, if you say that if you have an invertible matrix A, so if you remember the invertibility theorem, right? So from that concept, if A is an invertible matrix, then the columns of actually columns of A form a basis of Rn, because they are linearly independent, right? And they span Rn actually. Because when it is invertible, right? So remember that the determinant of A is not equal to 0, right? It means, and if you remember that theorem, that when there are linearly dependent vectors in A, this determinant is always 0, right? So columns of A form the subspace of Rn because they exist in Rn, and similarly, an example of identity matrix, let's say IN, which is an n cross n identity matrix in which the diagonal entries are 0. So let's say this is that, and this is 1 here, right? So the columns of identity matrix, we know that we already say this as I1 0 0 0 so on, E2 as 0 1 0 0, and similarly En as the last one, which is 0 0 0 0 1. Now they actually span the subspace. This actually span R of n, or all these vectors, their linear combinations actually span R of n, and normally that's why you use it as a standard basis for R of n. So it means if you want to show anything in an xy plane, so you say this is actually E1, this is actually E2. So when you write this as it's a standard basis, so it means this is a point 1 0, and this is a point 0 and 1. Okay. Now, so here this is a unit vector. You can think of this as a unit vector. Remember from your physics, elementary physics, this is actually a unit vector, and that's why you use it for the standard bases in Rn. So it means in this case it's R2. Similarly, if you have R3, you might have the third dimension here, which is E3, right? In this case this is 0 0 1, this is 1 0 0, and this is of course then becomes 0 1 0. Okay, now we can do another example. Let's say if v1 is equals to 3 0 and minus 6, and v2 is equals to minus 4 1 and 7, and v3 is equals to minus 2 1 and 5. So we have to determine if say these v1 v2 v3 is a basis of R3, right? So what you simply do here is try to find that the solution, and we know that we can do that. It means simply, in a sense, that you can write this as A as v1 v2 and v3, and try to look for the augmented matrix of the solution of 0. So it means we can say v1 v2 and v3, and you do the 0 column here. So if you put it here, which is 3 0 minus 6 minus 4 1 7 minus 2 1 5, and then of course here you have got 0 here. So you can think of this one here as doing the row operation on the third row, which is multiply this by 2 and add it here. So if I do that, that becomes actually 3 minus 4 minus 2, and then I have 0 over here, 0 1 1 here, and 0 here. So if I multiply by 3 and multiply by 2 and add it in the third row, that becomes 0 here. So that becomes minus 7 minus 1, and minus 4 plus 5, that becomes 1, and that becomes 0 again here, right? So in the third step, what we'll actually do is add this with this one here. So 3 0 0 and minus 4, when I add this here, it becomes 1 0 minus 2 1 2, and this is 0 0 0, right? So we can see here that this augmented matrix is actually consistent in a sense, and of course only possible solution that we have for this one is only when actually C, or let's say x1 equal to 0, x2 equal to 0, and x3 equal to 0, because here 2x3 is equal to 0, and when you put x3 equal to 0 in here, you get here x2 equal to 0, and similarly all of them are actually zeros. Okay, so it means it actually forms the columns of A form the basis of R3. Now similarly we can come to this point that how much vectors will be efficient to actually represent the vector space. So we say a basis is an efficient spanning set that contains no unnecessary vectors. Okay, now so let's say for example I got this sets v1 is equal to 0, 2, minus 1, and v2 is equal to 2, 2 and 0, and v3 is equal to 6, 16 and minus 5. So if you look at this set over here, we can see that actually not straight away obvious, but you can see that v3 is equals to 5 times v1 plus 3 times v2. So here you have this as in parametric form, and we know that if H is a vector space that is spanned by v1, v2 and v3, but the problem here is that v3 is actually can be written in form of the linear combination of v1 and v2. So effectively the span of this H is actually v1 and v2, because v3 is nothing but the linear combination of these two vectors, right? So that might exist in this span v1 and v2. So this span of v1, v2, v3 actually becomes span of v1 and v2, and that is so that means a basis. So spanning set theorem actually says that that a basis is an efficient spanning set that contains no unnecessary vectors. So in this case v3 is an unnecessary vector, and this is an unnecessary vector has to be get rid of, and now we can only have the basis of H, v1 and v2 as the basis of this subspace H. So let's formally define that spanning set theorem, that if S is a set of vectors v1 to vp in H in V, let's say in V, and that H is equals to span of v1 up to vp, right? So it says that if one of the vectors in S, say vk, is a linear combination of the remaining vectors in S, linear combination of the remaining vectors in S, then the set formed from S by removing vk still spans H, right? So what it say that if S is a set of vectors in vector space V, and H is a subspace defined by the span of these vectors, right? So if what I'm saying here is, if one of the vectors in S, which is v1 to vp, say let's say here it is vk, is a linear combination of the remaining vectors in S, then the set formed from S by removing vk still spans H. So that's what we just did in our previous example, right? That we removed v3 because it was a linear combination of v1 and v2. So these two vectors still span H, and that's what we generalize this example to an arbitrary p set of vectors. And the second part that is also quite important, which is if H is not equal to 0, it means there is not null space. So some subset of H is a basis for for H. Okay, so if we say if H is not equal to 0, so in this scenario some set of S is the basis for H, so there can be some possible set of vectors which are not linearly dependent can form the basis of H, right? The proof is given in the book, you can go and read that. So the thing here is so we can start with, say for example, if there are v1 to vp vectors, right? So if one of the vectors is independent, vk, we will remove that vectors from the basis vector. Similarly, we will keep continuing searching. Say another vector vj comes out and also linear independent, we will also cross them up. So we now have, say if they were p vectors, now we will have actually p minus 2 vectors in the vector space, and we keep continue that process until the spanning set is actually becomes linear independent, and that entry is actually becomes the basis for that H. So if the spanning set is reduced to only, let's say, one vector, right? So we have to make sure that it is non-zero, right? So if it is 0, then it becomes a linear independent dependent, and that means that set spaces cannot be spanned by that 0 vector, right? So the set spanning theorem has two parts. First part is that you can remove that linear dependent vector from the spanning set, and you can keep removing that, keep removing the process unless and until you have all the vectors as linearly independent vectors. Yeah. Now similarly, as we have already studied the column space and the null space of the vectors, we can actually find the basis for the column space and the null space, right? So let's say for an example, find a basis of column B where we know that B is equals to B1 to B5, which is 1 0 0 0 0, sorry, 3 zeros, and then you have 4 0 0 0 0 minus 0 1 0 0 2 minus 1 0 0, and you got 0 0 1 0, right? So these are 5 vectors. And now the thing here is, again from the set spanning theorem, we can actually see that I can write b4 b2 as nothing as 4 times b1. Similarly, I can write b4 as 2 times b1 minus b3, right? So since now these two vectors b2 and b4 can be written in terms of b1 and b3, we can now remove that vectors, and the column space of A spanned by the column space of A is nothing becomes span of b1, b3 and b5. Okay. And now if you remember that from earlier lectures, you know that when we're talking about determining the basis of the column space, so we said that the pivot columns of A of A form a basis of so we can see here we can identify the pivot columns, the number of pivot columns that we have. So in this case we only had 3 pivot columns, 1, 3 and 5. Okay. Now what we have to remember is a very important thing, that though the pivot columns are evident in the previous example, however in the previous example, because it has been reduced to echelon form, but we have to really be careful to use the pivot columns of A itself to form the basis of column A, because if you remember last time around, that row operations actually can change the column space of the matrix, because if you have zeros in the last row, it means any of the vectors that may have non-zero entries in the vector space cannot be written as a combination of the spanning set of the vectors. So say if you say this as, let's say, if you say this, the columns of an echelon form B of A are often not in column space of A. Say for example, in the previous example, this was the matrix A. Matrix B. Its row equivalent matrix is this matrix A, which is 1, 3, 2, 5, 4, 12, 8, 20, 0, 1, 1, 2, 2, 5, 3, 8, minus 1, 5, 2, 8. Now again, if you read the statement above, right, so the columns of an echelon form B of A, right, so should also write B? I think that will make things quite clear. 1, 0, 0, 0, and this is actually 4, 0, 0. Then you have minus 2, 1, 0, 1, 0, 0, and then you have minus 2, minus 1, 0, 0, 2, minus 1, 0, 0, and you have that as 0, 0, 1, 0. Okay. Now actually you can see here that that A has been reduced to B, right? So the columns of an echelon form of B, form B of A, are often not in the column space of A. We can see here, because if you take these zeros, right, so they are all zeros, right, in the last entries, and they cannot span the set of the column space of A, right? So what we have to be really careful in actually using the pivot columns of A itself to form the basis of A, because when you reduce into this echelon form, right, you might end up having the entries as 0. So any non-zero entries which can be made by the linear combination of these vectors, or the basis vectors of the column space of B, will not actually be relating to the vectors in A, right? So this has to be a very important point, and this is a quite an important point. And when you are trying to find the basis of column space of A, you have to be very particular about choosing the pivot columns. Now similarly, we can actually look another example from the spanning set theorem. Let's say so we were given this set of vectors, so let's say this is 1, 0, 0 and 2, 3, 0. Okay, So we can see here they are linearly independent, but they don't span R3. So linearly independent but don't span R3, right? Because we know for to span R3 we have to have three bases, three linear independent sets. Now let's do another example. Say 1 0 0 2 3 0 4 5 6, right? So we can see here that this is actually a linearly independent set and can be a basis for R3, right? Now let's say another example, which is 1 0 0, same thing here, 2 3 0 4 5 6 and 7 8 9, right? So same as we got previously got three vectors, now we got four vectors, and you remember that when the number of vectors are more than the number of dimensions in which the vector exists, one of the vectors bound to be at least one of the vectors bound to be linear independent. So it means you can remove one of them. Since we already know that this is a linear independent set, it means this vector can be written in terms of the linear combination of these three vectors. So it still spans R cube, but it is linearly dependent. So again we can do some problems here. Say for example, if I say v1 is equals to 1 minus 2 and 3, and v2 is equals to minus 2 7 and 9, so we have to determine if v1 v2 is a basis for R cube, is v1 v2 is a basis for R square, right? So so you can see here that first of all, to find a basis for R cube, what we have to do is to look for any linear dependence or independence relationship. So it means you can simply see here as 1 minus 2 3 minus 2 7 and 9. So you can do some kind of operations here. It means 1 multiply this one, 2 add here, 3 multiply and subtracted from here leads to 1 minus 2 0 0 3 0. It means they are actually linearly independent set. Now not every row of A contains a pivot position, so so the columns of A do not span R cube, right? So it means so they don't span R cube. Okay. Now by said by the above theorem that we have already discussed, if there is no possible, so if let's say I should write it, if hence v1 v2 is not the basis, is not a basis for R cube, because it must have to have at least three vectors to form the exact basis for R cube, or at least have to have at least three pivot columns to have this kind of R cube. Now the question is, the first part we have already answered that. The second part is v1 v2 is a basis of R square. First of all, what you have to look here is that v1 and v2 are not in R square, they are actually in R cube. Okay. So what you can say are that basically it means these vectors cannot actually form the basis of R square. Now one thing that can be could be possible, because they are linearly independent set, there might be a subspace that is defined by the span of this v1 and v2, right? And which this subspace exists in R3, right? Is a some part of R3, not exactly R3, is a some part of R3. Okay, now this is the only possible explanation that you have on this question. Okay, now say now there are four vectors v1. Let's say v1 is equals to 1 minus 3 4, and then you have v2 as 6 2 minus 1, v3 as 2 minus 2 3, and v4 is equals to minus 4 minus 8 and 9. So the question is, find a basis for the subspace. Find the basis for the subspace W spanned by v1 v2 v3 and v4. Right, now we can do again the same thing here as we did at the last time, but what you have to remember straight away looking at the question, we have to remember that the vector exists in 3 dimensions. There are 4 set of vectors. It means even these W spanned by v1 v2 v3, the one of the vectors will be a linear dependent vectors, right? So but still we are going to solve that. 1 minus 3 4, 6 2 minus 1 2 minus 2 3, minus 4 minus 8 9, and when you do some kind of row operations on that becomes 1 0 0 6 20 minus 25 2 4 minus 5 minus 4 minus 20 25. Okay, now again I can do the row operations here. I am left with the following. It is 1 0 0 6 5 0 2 1 0 minus 4 minus 5 and 0, right? So that you can see here the first two the columns of A are the pivot columns, and hence form the basis of we can say so W is nothing but is the column of A. You can actually say that because this is v1 and v2 and is the finite span of okay, before we do that, now hence v1 v2 is a form of basis of W. So W1 and W2. Know that the reduced echelon form of A is not needed because the thing here is you already located the pivot columns. So it means v1 and v2 are actually the basis of W, and as already told you that it is at least one of the vectors will be linearly dependent on the other vectors. But once we put that in figure, we found out that actually it was the case, and at least one vector was there, but we have actually got 2 here. So it means only v1 and v2 are the suitable set for basis for this W. Similarly, we can do another example. Say so let's say that v1 is equals to 1 0 0, v2 is equals to 0 1 0, and say h is equals to s as 0 and s in R, so it means it's a scalar quantity, it's a real number. Then every vector in H is a linear combination of v1 and v2. So it means any s as 0 is nothing but s times 1 0 0 plus s times 0 1 0. So what we been asked is v1 v2 a basis for h, basis of h, right? So if you look at the first problem that we did, um, um, so if you look at this example that we covered, so we can see here that neither